Today we're on page 3 of the chapter 14 AP Chemistry notes, and we're going to be comparing acid strength and comparing conjugate base strength. So here we have 4 acids, HCl, HCN, H2O, which can be considered an acid, and HF. We should remember that HCl is one of our strong acids, Hickel, Hibber, high, NO3, Hickel, O4, H2SO4, and these other acids would be considered weak acids. Let's review a little bit about equilibrium with acids. An acid is going to give you an H plus as well as the conjugate base of the acid. So this is the acid, this is the conjugate base of the acid. So when you do the equilibrium expression, which is a Ka, a special equilibrium constant for acids, you're simply going to take your products, H plus to the first, F minus to the first, over your reactant, HF to the first, and you're going to write your Ka expression. So nothing really new from what we had learned before about equilibrium. Now we're going to talk about the conjugate base specifically, this F minus. What happens if you were just to take some F minus, which would come from a salt, like let's say sodium fluoride, NaF, dissolve it in water, which you'd know is soluble because group 1s are soluble. So you'd have a bunch of Na pluses which do nothing, we'll just leave them out, and F minuses which will do something. Because when you put an F minus with water, it always wants to go back to being the weak acid. A weak acid, the reason why it's weak is because it wants to go together, the H and the F. So the F minus is going to forcibly take an H from the water, forming back HF, and leaving behind OH minus from the water, and that's what's going to make the solution basic. So this conjugate base makes water basic by taking an H, leaving behind an OH minus. Now you could write the equilibrium expression for this, which is now going to be called a Kb because it's for a weak base, and it's going to be products, each raised to their powers, over reactants raised to their powers, but we're going to leave out water because it's a liquid, so that's why we're going to get HF times OH minus over F minus. Now let's understand how to figure out which of these acids is the strongest. The Ka value tells you how strong an acid is. So if you have a very high Ka value, that would be because you have a strong acid, which means you have lots of products and very little reactants. Again, a strong acid is one that gives up its H pluses. It wants to break apart. It does not want to stay together. That's what makes it strong. It gives you lots of H pluses. So HCl is a strong acid, again, from our list. So pretty much the Ka of that is close to infinity, meaning that it breaks up 100%, so you're going to have almost an infinity of this, almost 0 of that, and so your Ka is going to be very, very large. But if you were to take something like HCN, hydrocyanic acid, it does not break up apart very much, nor does HF, and you can see that this equilibrium is actually going to favor the reactants because it's weak, so therefore it's going to have a very low Ka because it's going to have very few products and a lot of reactants. Okay, so Ka is a quantitative way of understanding how strong an acid is. So you can see from this list that the strongest acid is going to be HCl, followed by the next one, which is going to be HF, because this number minus 4th is going to be the next biggest, followed by number 3 is going to be, it's not really writing very well, HCN, and lastly would be water, which makes sense. You wouldn't expect water to be that much stronger than anything else if something else is an acid. So water is number 4, but it still could be considered to be a weak acid, like very, very, very weak, depending on with what you put it. All right, now let's talk about the conjugate bases, In order to understand this, let's go back to our reaction, and let's see if we add these two equations, if we add this equation and this equation, which reactants and products can cancel out. So you can see that the F minus can cancel out right here. You can see the HF cancels out right here, and you're left with simply H2O liquid at equilibrium with H plus aqueous and OH minus aqueous. Okay, so this is what we have left from our equation. And that should look familiar to you. That's the dissociation of water. Now remember what happens when you add reactions, you multiply their K expressions. So I'm going to remind you of this. You're going to multiply. It says multiply. Okay, so let's multiply this. We're going to have the first one, which is H plus concentration times F minus concentration divided by HF concentration. And then let's multiply that by the Kb, which is the HF concentration times the OH minus concentration divided by the F minus concentration. And you can cancel out, again, the F minuses. You can cancel out the HFs, and you're left with this H plus times OH minus, which should definitely make a lot of sense to you because that is the correct K expression for this equilibrium, which is Kw. So if you write Kw, which we learned before for water, it is equal to the concentration of H plus times OH minus. So this helps us to know a really good formula that we're going to need, that Kw, the constant for water, is equal to the Ka of a weak acid times the Kb of its conjugate base. This is a very important formula that we're going to use for these types of problems. Okay, so Ka of an acid, a weak one, times the Kb of the conjugate will always give you Kw. So let's go back up to the chart here and understand the conjugate bases. So the conjugate base of HCl is going to be Cl minus once it gives up an H plus. The conjugate base of this is going to be Cn minus once it gives up its H. Water is not applicable. I'll explain that in a second. And F minus is the conjugate base of HF. So why is this crossed off? Because when water breaks up, you could think of water down here as an acid because it gave you H plus, and you could think of it as a base because it gave you OH minus. So you could call water an acid, you could call water a base, either one. So as an acid, it has a Ka of this, and as a base, it's going to have a Kb also of 1 times 10 to the minus 14th, which I know doesn't make sense based on what we said down here, okay, about the Ka and the Kb, but this is water. This is not a regular acid or conjugate base. It's water that acts as both an acid and a base because it's amphoteric. So when water dissociates, you can call it an acid or call it a base. So here I'm calling it an acid, here I'm calling it a base. It has the same K because it's the same reaction. Now let's solve for the Kb for each of the others. So Kb is going to be equal to Kw over Ka. So I'll write the general equation here. Okay, and then we'll put the numbers in. So there's a W right here. So Kw is going to be 10 to the negative 14th. You're going to divide that by the Ka, which was pretty much infinity. All right, so you're basically going to get 0 as your Kb for Cl minus. Okay, next we're going to take 10 to the minus 14th for this, divided by the Ka, which was given, 6.2 10 to the minus 10th. And that's going to equal your Kb, which is 1.6 times 10 to the minus 5th. And then lastly, you're going to take your 10 to the minus 14th, which is Kw, divided by your Ka given of 7.2 times 10 to, whoops, sorry about that, 10 to the minus 4th. And you're going to find out that this one comes out to be a Kb of 1.4 10 to the minus 11th. So here we have our Kb's, and this is going to help us to compare the values and the strengths of the bases. So looking at this, our number one base is going to be the Cn minus, because this is the largest number out of all 4 of them. The second one is going to be the F minus, because that's the second largest. The third one is going to be the water, which is interesting. Okay, and the last one is going to be the Cl minus. So let's try to make some sense out of this. What we're saying here is that water is actually a stronger base than chloride. Water is a stronger base than chloride, which makes sense because when water dissociates, even though it's a tiny bit, it gives you a very little bit of OH minus. It does. So it does have some OHs floating around. However, when chloride goes into water, it does not react at all. It just sits there. Cl minus just sits there. It does not give you any OHs because it doesn't react with water like F minus would. Cl minus will not react with water at all because remember, HCl does not want to go together. It wants to stay apart. So this is the interesting thing, once again, that water is a stronger base than chloride, which means that water is a stronger base than the conjugate base of a strong acid. I'll say that one more time. Water is a stronger base than the conjugate base of a strong acid. That'll be true for all the strong acids. Okay, let's move ahead to the bottom of the paper, and this one will go a little faster because we got all our background information. So we're going to look at the strengths of these bases. We're going to go for the highest Kb. So of course, infinity is the largest, followed by the CH3NH2, followed by the NH3, followed by the H2O. Again, it makes sense that water would be the weakest out of all these. Now we're going to look at the conjugate acids. This is going to be not applicable for Na+, okay? So it's only going to be for the last 3. So the conjugate acid is once it gains an H+, this is going to be NH4+. Then this again is not going to count because remember water counts as both an acid and a base. And then this one is going to be CH3NH3 positive 1. So now this is going to be non-applicable over here because there is no conjugate acid, so that's never going to be asked of you. But we are going to find the the Ka for each of these by doing what we did before. So we're going to take Kw divided by the Kb of the base. So the Kb of the base is, I'll just write this here. So Kw is going to be 10 to the minus 14th. The Kb is going to be 1.8 10 to the minus 5th. And then what you're going to do is you're going to find the Ka of the conjugate acid. In this case, it's going to be 5.6 10 to the minus 10th. All right, next one is just going to be, remember, water is going to be 1.0 times 10 to the minus 14th. And lastly, this is going to be 10 to the minus 14th divided by the Kb, and the Kb was 4.38 10 to the minus 4th. So that's going to give you a final answer of a Ka of 2.28 10 to the minus 11th. So now we're going to compare these acids, and we're going to find out that the strongest one is the NH4+, which is going to be the ammonium, followed by number 2, which is called methyl ammonium, and lastly is going to be water in this order here. Okay. Lastly, I wanted to mention this, which I hadn't mentioned in a previous video, the names. So we should know that NH3 is called ammonia, and the NH4+ is called ammonium, which is, as we said, a weak acid. Okay, now by a similar way, the name of this CH3NH2 is called methyl, which is the CH3 because it has one carbon, and amine is the NH2. Whereas this is called methyl ammonium. And even though the ammonium doesn't have 4 H's, it has 3 H's, that has to do with the Lewis structure. So I'm going to show you the Lewis structure briefly. If you do NH3, NH3 is going to be an N with an H here, an H here, and an H here, and a lone pair. Along comes an H+, which has no electrons, and so the ammonium can form what we said before was a coordinate covalent bond, and that's what NH4 plus is going to be. Now if you had methylamine, methylamine has a C with 3 H's because you have to connect to the N, so they can only put 3 H's on the C. And then the N is going to also have a lone pair, but it can only connect to 2 H's. That's why it's not like NH3, it's NH2 because it's connected. Along comes an H+ with no electrons. And again, you can form what we call the coordinate covalent bond to make methyl ammonium. Okay, so the final structure, this is not really working here very well. The final structure is going to be that. And that's how you get the Lewis structures of these organic acids and bases.